Hello everyone, my name is Amanda Tolk. Welcome to our clinical education webcast. I'm delighted today to welcome Tom Murray of the Hull University Teaching Hospital, where he holds the position of lead physicist for superficial treatments. Tom will be giving a presentation on their experience of developing an internal eye shield for patients undergoing superficial radiotherapy. The availability of internal eye shields in the UK has been a major problem in recent years. In today's session, Tom will describe his group's appraisal of the available options and their input into the design and also the validation of the new KV eye shields. I have a few housekeeping items before I turn it over to Tom. This session has been recorded and will be available on our website if you'd like to review it at a later time or share it with a colleague who was unable to attend today's session. After the presentation, we'll be answering questions that have been submitted through the GoToWebinar chat window. If you have any questions, please do go ahead and enter them at any time, and I will moderate those at the end of the presentation. Thank you for joining, and with that, I hand over to Tom for today's presentation.
Thank you, Amanda. So, as Amanda said, I'm Tom. I'm the principal physicist for superficial at Castle Hill Hospital, which is part of Hull University Teaching Hospitals in the UK. So as Amanda alluded to before, there's been quite a difficult situation over recent years with the availability of internal eye shields in the UK. And this culminated in the UK's main supplier of eye shields stopped trading around 2020. And from looking at other things on the market, they were either not UKCA marked, which was the former CE marking, or things that did exist lacked an available sterilisation method. So the situation in Hull was we used to use a main supplier in the UK who made a single patient eye shield. So this was a device that you would disinfect for a single patient and then throw away once that patient's treatment had completed. We have a fairly low but very unpredictable uses of eye shields. And for that reason, we had quite a sophisticated stock control system of every time we finished a pack, we looked to see if we had another one in stock. If we didn't, we ordered a new one. And we found the situation in December 2020 that we had run out of our in-use pack of eye shields. So we only had a reserve one in stock. And at that point, we discovered that we were unable to order any eye shields. So what we did was we had a look at the options available to us in the market to change supplier to something we could proceed with. Because of the complexity surrounding it, we even started looking into electron eye shields as well. So the first ones we looked at were these tungsten eye shields with aluminium caps. Not specified for use with KV, but the fundamental characteristics of them means that they probably would be okay with KV. The issue that we had with those was the autoclave instructions varied from UK standards, and that was sufficient enough for our sterile services department to say that they were unable to process them. They were also not CE or UKCA marked, and that caused quite a lot of trouble in terms of purchasing. So the next option we looked at were silver-plated eye shields. These again were made by the same manufacturer as the previous one. They had an option for performing disinfection in between fractions for a single patient. That uses this Sidex OPA stuff, and working with our sterile services department, there were quite a lot of issues with the health and safety around doing those. So they trigger in the UK what would be called a COSH assessment. So it's not quite so simple to use them. Again, the autoclave instructions were different to what the UK standard ones are, and that causes issues for our sterile services department. Again, we're not UKCA marked or CE marked, and because these have no kind of low density coating, we would need probably to coat these in wax, and I'll talk about this in further details later on. The final item that we looked at was these tungsten eye shields. So these were manufactured by Civco, sold through a UK distributor, technically for electrons, but we thought they would probably be sufficient for KV photons. Main issues around those are they use gas sterilization, but at the time of inquiry, these were CE marked. So these were what we started looking at going through. Gas sterilization is with use of ethylene oxide, and it's specifically for delicate medical instruments, so things that you can't really put through an autoclave. It's quite controversial in its use, but there's a really good document here that I've put a link in from the Royal College of Ophthalmologists that gives a very pragmatic view of the fact that this type of sterilization isn't necessarily ideal for prion diseases. However, they appreciate the fact that it probably is the best you can do, and it weighs up the consequences of if you have no other option, then gas sterilization is acceptable. Unfortunately, no UK hospitals seem to have this as a service, but we did manage to find an external supplier that could do gas sterilization. So we got everything in place, and the winner, we were going to procure these eye shields, and then by the time we got round to getting all our procurement in place, they were no longer CE marked by the time we got to order. And we were warned about this by the distributor, but we weren't willing to order them without establishing that we could sterilize, we could use properly. And ultimately, on review, is if they were near the point where they were no longer going to be CE marks for us, it potentially wasn't a long-term solution. It was just delaying the inevitable situation where when we go to resupply, we would have been able to do them. So we started asking for help. So we engaged in the UK community. So a lot of UK centres, we all essentially worked for the same employer, for the National Health Service. So we asked around with the community of what other centres were doing. And everybody was largely in the same position of running on depleted stock or had already run out. Through these calls to the community, we were also approached by a manufacturer for pure imaging phantoms, and they make bespoke radiotherapy test objects, and they offered to begin the manufacturing process to become a supplier of internal eye shields. So the work that we had done over the last 2 years trying to find a suitable eye shield actually turned out to be quite useful, because we were able to use this information to build up a specification for what we needed. So the specification we said that these eye shields must be able to achieve is they must be sterilizable by a UK method or disposable. So either would be fine by us. They must be suitable for KV photons up to 120 kV, and that rather selfishly is the maximum energy that we would use for treating things around the eye, and ideally suitable for electrons up to 6 MeV, but this wasn't a necessity. A big part of this was we wanted them sufficiently coated to reduce backscattered dose, and I will talk about that more in a second. And ultimately, they must be UKCA marked, otherwise we'd been able to purchase them. So, as I keep alluding to, is in a normal KV beam, is when we look at a depth dose curve, we get a photon that's traveling through a medium, depositing energy as it goes through, and we get a depth dose curve where we deliver a high dose to the surface, and then it falls off as we go through. What we ideally would like is if we put in a piece of lead into the path of the beam, is for the dose in front of the shield to be completely undisturbed, so we deliver exactly what we were giving before, and we give no dose beyond it. but the universe is never that kind. So there's quite a lot of research that's been done into the effects of dose surrounding interfaces of high Z materials. So what effectively happens is this photon comes in and then immediately it interacts quite heavily with the high atomic number material. And the consequence of that is you get a lot of really localized scatter around that interface. So the dose directly next to the shield becomes quite high, and actually you lose scatter towards the entrance of the beam. So I've done a overzealous artist's impression of this effect. So we can see is as you enter the patient is you'd be giving less dose than you previously gave, and directly next to the shield you give significantly more. So the easy way to prevent this from occurring in terms of a untoward dose to the patient is to put a thin layer of tissue equivalent material around that lead shield, and what that will do is that will absorb the low energy scatter that's produced on the shield itself, and then you will still face a reduction in dose upstream of the shield, but you are avoiding that high dose, which could have serious clinical impact. So the first revision that we made of this is we look towards the electron side of things, so something that would work with both. So we made a 2mm tungsten shield, and that was surrounded by 1mm of acrylic. As we started to look into this, it was quite expensive to produce. Tungsten's quite an expensive metal to procure and difficult to machine. This would have needed gas sterilization as well, which incorporated a lot of problems and would have been an issue for a lot of UK centres. Just on a learning point with us and the manufacturer as well is when I gave the specifications of the size that we were going to use is I hadn't particularly been clear with what I meant. So what we ended up with is a hemisphere, when actually what I wanted was a spherical cap. So this was an interesting thing for both of us to go through, and kind of the specification of how do we give the sizes of these shields, because as you get bigger, it sort of depends. The construction between the outer layer of acrylic and the tungsten, I didn't think it was necessarily going to work too well. It got damaged fairly easily, and with that it would allow ingress of dirt. So we coiled back on the electron idea with revision 2 and produced a 2mm thick lead shield with an epoxy resin coating. This was pretty cheap to produce and could be single patient use. In the initial production of this, we generally thought the coating was too thin, and because it was clear, it was very hard to tell whether the coating was complete or not. So this coating that we put on provides a sanitary surface, and also it's there to absorb that really low energy localized scatter. And we saw that effect in, actually, if we put a chamber directly under this, we saw quite a high level of transmission, so about 40% transmission. Just putting one sheet of acetate paper in between the chamber and the shield reduced that down to basically an unmeasurable level. So it showed that this probably wasn't clinically relevant, but for other reasons as well, is ideally the coating would be thicker. So in revision 3, we were very happy. We got a thicker coating. It was also coloured, so it was very easy to see if you have any defects in it. So that's much more useful for when we're treating, as in day to day, we can see if there's any damages to it. And because no great invention has been made for suspending eye shields over plotting tanks, you can see here we've done a beautiful arrangement with some transport tape and with the eye submerged to kind of approximately the depth that we thought it would be in kind of an eye. So the eye shield ever so slightly submerged, so the water on top is simulating the thickness of an eye shield. And what we found with that, with our 60 kV beam, we got a transmission of around 5%, and at 120 kV, about 10%. And the backscattered dose, which is the dose measured upstream of the shield, we kind of got a 3 to a 5% dose reduction, which is similar to what we expect to see before. So plotting those is what we have here. Is in the blue line is our unshielded normal 60 kV measurements. So these are all actually just ionization measurements. They haven't been corrected to dose, but they do show kind of the effect of the shield. So directly underneath the shield, we got a dose reduction, but we start to see as scatter re-establishes, this dose actually does start to increase very slightly under the shield. And if we look at profiles of this, we can see quite clearly the effect of popping the shield in the beam. So in this image on the left, we have our profiles with depth for a normal field that without a shield in. In the second image, we have the profiles with the shield in place. This effect is far more noticeable at 120 kV. So directly underneath the shield, we're attenuating the dose to around about 10%. But actually, as you start to go to greater depths towards around 2 centimeters, your dose actually starts to increase back up to where it was. And again, if we look at these profiles, you can quite clearly see that this is basically a re-establishment of scatter in the middle areas. And originally we had looked at this because I was slightly unhappy with a transmission of 10% through the shield at 120 kV. But actually what we discovered is if we made this shield thicker, it actually made very, very little difference to the dose underneath it. And that's basically because the dose you're getting underneath it is coming from the scatter from the unshielded areas of the beam. If you use a larger shield, this effect, the shielding effect actually becomes better. So it's just to take in mind as when you're using these, there are advantages in using larger shields. Clinically, we would usually be using 60 kV in these situations, so it's not necessarily that important, but it's something to be aware of. So from this is kind of my impression of when internal eye shields are actually useful. So from the data I presented, they're basically only useful if you want to protect structures directly under them. So, and just to raise the point on them is an internal eye shield probably shouldn't be used if the eyelid isn't involved. You should really be using external shielding. A consideration of is actually the dose to structures directly under it do start to get slightly higher as you go down. So the cornea and the lens is the structures that you're primarily protecting. So as scatter re-establishes, they become less useful. And if you're dealing quite high doses, 15–20% of, if you're doing a 60 grade prescription, can be fairly significant. And just a caveat generally with all of this, that the presence of high atomic number materials in radiation fields has very complicated effects. So we've done measurements here, but there'll be a very large degree of uncertainty when we're dealing with low energy scatter around high atomic number materials. And that's generally something to consider when you're treating, is while you are putting a shield in and it is shielding areas below it, you do need to be mindful of what you're doing to the dose in the areas that you're actually trying to treat. And it is a very complex thing to work out. So that's in mind. I'd like to say a big thank you for Pure Imaging Phantoms, Extral and Tristal, whose expertise in this area have been invaluable in progressing the project. So Extral is now the distributor of the eye shields and they're available now. The only conflict of interest we've got is we received a small discount on our order of internal eye shields. And before I hand over for questions, please be kind and know that I'm not an expert in medical device manufacturing, sterilization, or any of the legal structure surrounding medical device registration. This project I've got involved with has thrown me more into that area than I ever wished or ever want to get involved with ever again. And so I'm going to hand over to Amanda now, who will facilitate questions and answers.
Oh, thank you very much, Tom. That was a very informative presentation, and I happen to love all the technical aspects of it. So there are a few questions, some of which are technical, Tom, so I'll direct them at you if that's okay. Did you do any transmission measurements above 120 kV? And if not, why?
So generally, as talked about before, is clinically we wouldn't use such a high energy for stuff around the eyes, so we didn't feel the necessity to measure anything around there. The other issue around that is kind of the setup ends up being slightly more difficult because you end up having the closed-ended applicators. So were we to ever use it, we would look into it, but I can't see any clinical need to do so.
Okay, brilliant. And I assume also that if somebody wanted to do above 120 kV, they could contact you and follow your protocol for how you did your measurements so eloquently.
Yeah, I'm happy to speak to anybody who wants to. I've had people contact me previously about it, asking if we did go up there, and my response back has been what do you treat with such high energies? I expect, I mean, there's a gradient of this, isn't there? So people will be doing like 130, 140. I mean, we stopped at 120 because that's the clinical energy we run at 3 clinical energies, and it's one of the ones we operate, but it's not going to be significantly different if you're 10 or 20 kV on top of that.
Okay, another question is, what do you plan to do, if any, on QA as you get new batches of the eye shields in? Because you obviously validated the first. Do you have any protocols that you're going to implement in the centre for using them going forward?
Yeah. So because these are effectively a disposable item, you don't want a huge onerous amount of QC on them. The most important side of things is kind of your pre-treatment checks, and that should be done every single time you use them, checking for scratches, checking for any deformation of them. Otherwise, when we get a new batch, we take one of each size from the batch, and we quickly measure a transmission using a thin window 23442 chamber, usually with just a little bit of acetate over the top.
Okay, and I know you are the physicist, but have you had any feedback from the clinical staff on how they found using the new devices?
Okay, so as luck would have it, as I alluded to in my previous comments, is we have a very erratic use of eye shields, and actually since these have become available, we haven't actually had any patients requiring internal eye shields, which is always the way, but we are prepared. As part of these as a clinical assessment, we've had the radiographers look at them. They are actually very similar to what we used previously, so we're relatively happy, but actually we haven't had a patient so far.
We'll catch up on that topic in the next webinar, I'm sure, Tom. Another question that's come in, what sizes are available? Tom, I'm not sure how many sizes you validated, but I know from an extra perspective, we have 4 that have an internal radius from 12 millimeters up to 16 millimeters. Did you have any experience of all the 4 sizes when you were looking at your validation exercise?
So the validation exercise was performed on the smaller size. So I would expect the results to be there would be far less transmission with the bigger sizes.
Okay, perfect. The next question we have in is, can we buy them if we're not based in the UK? Absolutely, they are CE marked and they're available outside of the UK via Extral. You're more than welcome to contact us via the website. No problem at all. Looking at the questions, thank you, Tom. That's all the questions that we've had in this evening. Thank you for a very informative presentation. And if anybody has any other questions, please do contact Extral via the website or the email address, which is shown on the last slide. Thank you for your attendance, and we can close the webinar now.